Now, in this lecture, we find out the radius of the small circle. In the drawing, we have a quarter circle. A or B is a quarter circle. Inside this quarter circle, we have this semicircle and this small circle. And our mission is to find out the radius of this small circle. That is to say, our mission to find out the value of r, that is the radius of this small circle. In addition, we know that the radius of the big quarter circle is equal to 16 units in its length. So AO and OB, they are both the radii of this quarter circle. That is equal to 16 units in its length. Okay, repeat again, our mission is to find out the radius of this small circle. So first of all, we will define the relevant points to this question with letters. We define the center of this semicircle, this point is point P. We will define the center of this small circle, this point is point Q. We will define the point of tendency of tangent OB with this small circle, this point is point M. We will define the point of tendency of this semicircle with this small circle, this point is point S. And finally, we will define the touching point or the point of tendency of this small circle with the big quarter circle. This point is point T. And we know that AOB is a quarter circle, therefore this circle must be equal to 90 degrees in its size. That is to say, angle AOB must be equal to 90 degrees because AOB is a quarter circle. The radius AO of the quarter circle equals to 16 units in its length according to what is given as the question. Here, actually, the radius of this quarter circle is the diameter of this semicircle. Again, the radius of this quarter circle AO is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to 16 units in its length. Therefore, the radius of this semicircle must be equal to half of it. It must be equal to 16 over 2, that is 8. So the radius AP of this semicircle equals to 8 units in its length. Likewise, the radius PO is also equals to 8 units in its length. Here we have the radius QM that is equals to R, that is the radius that you are looking for in this question, is drawn to point M, that is the point of tendency of tangent OB with this small circle. So here we can implement rule 1. According to rule 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have in the drawing a circle, and we have tangent AB that is tangent to this circle at this point, point M. And we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, It means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius QM that is equal to R. The radius QM is drawn to point M, that is the point of tendency of tangent OB in this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MO. If OB is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction. That is to say, from the center of this small circle, that is to say, from point Q, we will draw perpendicular on AO. Again, from point Q, we will draw perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point Q inside AO, this point as point H. By doing this construction, we created here quadrilateral HQMO. Inside this quadrilateral HQMO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the quadrilateral HQMO, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral HQMO as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side QM must be equal to the opposite side HO. But QM equals to R, therefore HO must be also equal to R. What is the length of line segment PH? The length of line segment PH equals to PO minus HO. Again, PH equals to PO minus HO. I write it down. PO, actually PH, this is line segment PH, this is equals to PO minus HO. So PH equals to PO minus HO. So PH equals to PO. PO is 8 minus HO. HO is R. So in total, PH equals to 8 minus R units in its length. This is line segment PH, and it is equals to 8 minus R units in its length. So I write it down. In the drawing, we have this semicircle touches this small circle at point S. Actually, the semicircle has an external notch with this small circle at point S. So, in other words, you can say that the semicircle and the circle, the semicircle and the small circle touch each other externally at point S. they have between them external notch at point S. So here you can, whenever you have an external notch between two circles, you can implement rule 10. Repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So here we have those two circles. The center of this circle is at point O, the center of this circle is at point M. And the straight line that connects their centers together is of course the straight line OM. So according to this rule 10, the straight line OM must pass through point P, that is their touching point. OPM is one straight line. Again, OPM is one straight line. Okay? We can implement rule 10 in our drawing. In our drawing, the small circle touches the semicircle externally at point S. So they have an external notch between them at point S. And therefore, according to rule 10, we know that the center of this semicircle is here at point P. The center of this small circle is here at point Q. According to rule 10, the straight line that connects the centers together, that is to say the straight line PQ, must pass through point S, or PSQ is one straight line. Again, PSQ is one straight line. Repeat again. Here, the straight line that connects their centers together, PQ, passes through point S, or PSQ is one straight line. Okay. But what is the definition of line segment PS? Line segment PS starts from point P, that is the center of the semicircle, and ends at point S, that is the point on the semicircle itself. This is exactly the definition of a radius. Therefore, PS is the radius of this semicircle that is equal to 8 units in its length. PS equals to 8 is the radius of the semicircle. What is the definition of line segment QS? Line segment QS starts from the center of this small circle, that is to say from point Q, and ends at point S, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle that is equal to R. And because of the fact that according to rule 10, PSQ is one straight line, if PSQ is one straight line, it means that PQ equals to PS plus SQ. Repeat again, so PQ equals to PS plus SQ. That is to say, PQ equals to PS, that is 8, plus SQ, that is R. So in total, PQ equals to 8 plus R units in its length. Okay. So in the next step, I will copy the right green triangle PHQ. This is the right green triangle PHQ. And we'll implement the Pythagoras theorem on this right green triangle PHQ. Here by PT, is the variation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. PH side PH of the right triangle PHQ equals to 8 minus R. R is the radius that you are looking for, it is the radius of this small circle. The hypotenuse PQ equals to 8 plus R. Here PQ equals to 8 plus R. And HQ of the green triangle is the missing side, so we leave it as it is. So actually, this is the right green triangle PHQ that comes from the original drawing. According to the Pythagoras theorem, in this right triangle PHQ, PQ square equals to PH square plus HQ square. Again, PQ square equals to PH square plus HQ square. So write it down. So PQ square equals to PH square plus HQ square. PQ equals to 8 plus R, therefore PQ square is 8 plus R square, and it is equals to PH square. PH equals to 8 minus R, therefore PH square is 8 minus R square plus HQ square. HQ is the missing side, so we leave it as it is. According to equation 1, we should find out that 8 plus R square equals to 8 minus R square plus HQ square. Here we open the brackets on both sides of this equation, equation 1, and we get that 8 plus R square equals to 8 squared, that is 64, plus R square, plus 2 times 8 is 16, times R. In the other side of equation 1, we have 8 minus R square. Actually, 8 minus R square equals to 8 squared, that is 64, plus R square, minus 2 times 8 is minus 16, times R. So we have minus 16R plus HQ square. So here we have 64 on both sides of this equation 1, so 64 will get cancelled. And we have also R square on both sides of this equation 1, so R square also will get cancelled. After cancelling those two expressions, 64 and R square, in this side of equation 1 we left only with 16R, and on the other side of equation 1 we left with minus 16R plus HQ square. So according to equation 1, 16R equals to minus 16R plus HQ square. Here we add 16R to this equation 1, and we get that according to equation 1, 16R plus 16R is 32R, so 32R equals to HQ square. Here we substitute 32 by 16 times 2. And get that 16 times 2 times R equals to HQ square. Here we take a root out of this equation, equation 1, finally we get that HQ equals to the square root of 16 is 4 times the square root of 2r. So inside the root we left only with 2r. So in total we found out that HQ equals to 4 times the square root of 2r. This is side HQ, that is equals to 4 times square root of 2r. But we already found out that for the other HQMO is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side MO, but HQ equals to 4 times square root of 2r, therefore QM must be also equal to 4 times square root of 2r. So write it down, QM equals to 4 times square root of 2r. Here, the small circle touches the big quarter circle at point T. Point T is the point of tendency of this small circle with the big quarter circle. Actually, they touch each other internally at point T. Therefore, they have an internal notch between them at point T. Whenever we have an internal notch between two circles, then you can implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching points. So in the drawing we have, this is the small circle that touches the big circle at point P. The center of the big circle is 0 at point O. The center of this small circle is 0 at point M. The straight line that connects their centers together, it is of course the straight line OM. So according to this rule 9, the straight line OM must pass through point P. That is their touching point. Or OMP is one straight line. Again, OMP is one straight line according to this rule 9. We can actually implement rule 9 in our drawing. Why? Because in our drawing, so as I mentioned before, the small circle has an internal notch with this big quarter circle at point T. That is to say, they are touching each other internally at point T, and therefore I can implement rule 9. The center of the big quarter circle is 0 at point O. The center of this small circle is 0 at point Q. So the straight line that connects their centers together is the straight line OQ, and according to rule 9, the straight line OQ must pass through point T, or OQT is one straight line. OQT is one straight line according to rule 9. So we join points O and Q together by straight line, and according to rule 9, the straight line OQ must pass through point T, that is their touching point. So see, on the drawing, the straight line OK passes through point T, that is their touching point. But what is the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and ends at point T, that is the point of the quarter circle itself. This is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle. This is equal to 16 units in its length according to what is given in the question. So I write it down. The straight line OT is the radius of the quarter circle. This is equal to 16 units in its length. What is the definition of line segment QT? Line segment QT starts from point Q, that is the center of this small circle, and ends at point T, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle. This is equal to R, according to what is given as the question. And according to rule 9, PQT is one straight line. And because of the fact that PQT is one straight line, it means that OQ must be equal to OT minus QT. Again, OQ must be equal to OT minus QT. So I write it down. OQ must be equal to OT minus QT. So OQ must be equal to OT. OT is 16. It is the radius of the quarter circle that is equal to 16 units in its length. Minus QT. QT is the radius of the small circle that is equal to R. So in total we found out that OQ equals to 16 minus R units in its length. Line 7, OQ equals to 16 minus R units in its length. In the next step, I'll copy the blue right triangle OQM in a new page, and we'll implement the Pythagoras theorem on this blue right triangle OQM. Here by PT is the version for Pythagoras theorem. Side OM of the blue triangle equals to 4 times square root of 2R. We just right now found out that the hypotenuse OQ of the blue triangle equals to 16 minus R. And it is given as the question that QM equals to R, it is the radius of the small circle. Roughly, this is the right blue triangle OQM that I copied from the original drawing, opposite to the Pythagoras theorem. In this right triangle OQM, OQ square equals to QM square plus OM square. Repeat again, OQ square equals to QM square plus OM square. So I write it down. This will be equation 2, according to equation 2. OQ square equals to OM square plus QM square. OQ equals to 16 minus R, therefore OQ square equals to 16 minus R square, and it is equal to OM square. OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square plus OM square. OM is R, therefore OM square is R square. So according to equation 2, we found out that 16 minus R square equals to 4 times square root of 2R square plus R square. Here we'll open the brackets on which both sides of this equation and equation 2, and finally we get that according to equation 2, 16 minus R square equals to 16 squared, that is 256, plus R square, minus 2 times 16 is 132, times R, so it is 132R, and it is equals to 4 times square root of 2 square. 4 square is 16, and square root of 2 square is 2. It is 4 times square root of 2r square. So 4 square is 16, and square root of 2r square is 2r. Why? Because the power cancels the root, and we have to only with 2r plus r square. Here we have r square on both sides of the equation. 2, therefore r square gets cancelled. So cancelled r square in this side of equation 2, you're left only with 256 minus 32r equals to 16 times 2r is 32r. So according to equation 2, we found out that 256 minus 32r equals to 32r. Here we add 32r to this equation, equation 2. And again, according to this equation, equation 2, 256 equals to 32r plus 32r is 64r. So here we divide this equation, equation 2 by 64, and finally get that according to this equation, equation 2, r, that is the radius of the small circle, the radius that we are looking for equals to 256 over 64, that is 4 units. So we found out that the radius of the small circle, the radius of this small circle, r equals to 4 units in its length. So in the next step, I'll summarize the lecture. In this lecture, I found out the radius of this small circle is equal to r. We found out the value of r. So in the drawing, we have a quarter circle. A or B is a quarter circle. And we know that actually the radius AO of this quarter circle equals to 16 units in its length. OB is also the radius of the quarter circle. That equals to 16 units, of course. In addition, we know that inside this quarter circle AOB we have this semicircle and this circle. And our mission is to find out the radius of this small circle that is equal to r. So first of all, we defined the relevant points to this question with letters. We defined the center of this semicircle, this point as P. We define the center of this small circle, this point is Q. We define the point of tendency of tangent OB with this small circle, this point is point M. We define the touching point of this semicircle with this small circle, this point SS, this point S. And finally, we define the point of tendency of this small circle with this quarter circle, this point is point T. We know that AOB is a quarter circle, therefore this circle equals to 90 degrees in its size. AO is the radius of the quarter circle, that is equals to 16 units in its length. So we know that AO equals to 16. According to what is given us the question, because according to what is given us the question, the radius of the quarter circle equals to 16 units in its length. But the radius AO of the quarter circle is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to 16 units in its length, and therefore the radius must be equal to half of it. It must be equal to 16 over 2, that is 8. So the radius AP of this semicircle equals to 8 units in its length, and the radius PO also equals to 8 units in its length. Okay. Here we can implement rule 1, because we have tangent OB is tangent to this small circle at this point, point M. We have the radius QM of this small circle that is equal to R. that is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever you have a radius that is drawn to the point of the tendency, then tangent OB must be perpendicular to the radius MQ. If OB is perpendicular to MQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, in the next step actually we did a construction. That is to say, from point Q, that is the center of this small circle, we draw perpendicular on AO. Again, from point Q, we draw perpendicular on AO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO, this point as point H. By doing this construction, we get the quadrangle HQMO. Inside this quadrangle HQMO, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle HQMO we have 4 rectangles. And according to rule 6, any quadrangle that has 4 rectangles must be a tetrahedron flat square. Again, any quadrangle that has 4 rectangles must be a tetrahedron flat square. So we relate to this quadrangle HQMO as a rectangle because it has 4 rectangles. But we know that the opposite sides of a rectangle are equal to each other. So a rectangle HQMO, side QM must be equal to the opposite side edge O. But QM equals to R, it is the radius of the small circle, that is equal to R. So PQ must be also equal to R. So if I don't, actually, therefore edge O, the opposite side edge O must be also equal to R. According to the rule, the opposite sides of a rectangle are equal to each other. So what is the length of this line segment PH? From the drawing it is very easy to see that PH equals to PO minus edge O. Again, PH equals to PO minus edge O. So PH equals to PO, that is 8, that is the radius of the semicircle, that is 8, minus edge O. We just right now found out that edge O equals to R. So in total, PH equals to 8 minus R. Again, the length of this small line segment, PH equals to 8 minus R. So here, this semicircle touches this small circle at this point, point S. That is to say, they have an external notch between them at point S. So they are touching each other externally at point S. Whenever you have an external notch between two circles, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. So here two circles. Those two circles touch each other externally at point P. It's point P. So those two circles have an external between them at point P. The center of this circle is at point O. The center of this circle is at point M. And the straight line that connects their centers together is of course the straight line OM. So this straight line OM, according to rule 10, must pass for point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So can I actually implement rule 10 in our drawing? One put in our drawing, this semicircle and an external notch between this small circle, that is to say it touches this small circle at point S. Point S is the touching point of this semicircle with this small circle. So they have an external notch between them at point S, and therefore the straight line, actually the center of this semicircle is at point P. The center of this Small circle is a point Q. So the straight line that connects the centers together is the straight line PQ. So according to rule 10, the straight line PQ must pass through the touching point, that is point S, or PSQ is one straight line. Again, PSQ is one straight line. So here, what is the definition of line segment PS? Line segment PS starts from point P, that is the center of this semicircle, and ends at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that is equal to 8 units in itself, according to what is already found out. What is the definition of line segment QS? Line segment QS starts from point Q, that is the center of this small circle, and ends at point S, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle, that is equal to R. So in total, because of the fact that PSQ is one straight line according to rule 10, it means that PQ will be equal to PS plus SQ. Again, PQ will be equal to PS plus SQ. So PQ equals to PS. PS is 8 plus SQ. SQ is R. So in total, PQ equals to 8 plus R. PQ equals to 8 plus R. In the next step, I copied this right triangle PHQ in the new page and implemented the Pythagoras theorem on this right triangle PHQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle PHQ that I copied from the original drawing. So according to the Pythagoras theorem, in this right triangle PHQ, PQ square equals to PH square plus HQ square. Again, PQ square equals to PH square plus HQ square. PQ is 8 plus R, therefore PQ square is 8 plus R square, and it must be equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. HQ is the missing side, so we leave it as it is. Here, open the brackets on both sides of this equation, equation 1, and find out that according to equation 1, 8 plus R square equals to 8 squared, that is 64, plus R square plus 2 times 8, that is 16, times R. So it is plus 16R, and it is equals to 8 minus R square. 8 minus R square equals to 8 squared, that is 64, plus R square minus 2 times 8, that is minus 16, times R. So it is minus 16R. Plus HQ square. So here we have 64 on both sides of this equation 1, so 64 will get cancelled. And we also have R square on both sides of this equation 1, so R square also get cancelled. After cancelling those two expressions, what is left from equation 1? In this side of equation 1, we left only with 16R, and the other side of equation 1, we left only with minus 16R plus HQ square. So according to equation 1, if we found out that 16R equals to minus 16R plus HQ square. Here we added 16R to this equation 1. If I found out that according to equation 1, this equation 1, 16R plus 16R is 32R. So 32R equals to HQ square. Here we substitute 32 by 16 times 2. So according to equation 1, 32 that is 16 times 2 times R equals to HQ square. Here we took the root out of this equation 1, if I found out that HQ equals to the square root of 16, that is 4, times the square root of 2R. So inside the root, we have only with 2R. So if I found out that HQ equals to 4 times square root of 2R. So this side HQ equals to 4 times square root of 2R. We've already found out that quadrilateral HQMO is rectangle and the opposite sides of rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side OM. But HQ is 4 times square root of 2R, therefore OM must be also equal to 4 times square root of 2R. So here we have this small circle, and an internal knot with this big quarter circle. That is to say, it touches the big quarter circle here at this point T. So the small circle have an internal knot with this big quarter circle. Whenever we have an internal knot between two circles, you can implement rule 9. A bit quicker on rule 9, according to rule 9. If two circles touch each other internally, then the straight line that connects their centers together passes through their touching points. So here we have a big circle and a small circle. They touch each other internally, it's point P. That is to say, they have an internal arch between them, it's point P. And therefore, according to this rule 9, here we have the center of this big circle is at point O. The center of this small circle is at point M. And the third line that connects their centers together is the third line OM, of course. So this third line OM must pass through point P according to this rule 9. Repeat again, the third line OM must pass through point P, that is their touching point. Or OMP is one third line. Again, according to this rule 9, OMP is one third line. Can actually implement rule 9 in our drawing. Well, because in our drawing, so, as I already mentioned before, we have it's point T, the small circle touches the big quarter circle, that is to say, they have it's point T and internal arch between them, therefore, and you know that the center of the big quarter circle is at point O, the center of this small circle is at point Q. So the third line that connects their centers together is the third line OQ, must pass for point C, that is their touching point. Or OQT is one third line. Again, OQT is one third line. If OQT is one third line, it means that OT is also one third line. But what is actually the definition of the third line OT? The third line OT starts from point O, that is the center of this quarter circle, and then the point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle that is equal to 16 units in its length. According to what is given as the question, OT equals to 16. What is the definition of line segment QT? Line segment QT starts from point Q, that is the center of this small circle, and then at point T, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle that is equal to R. And because of the fact that OQT is one straight line according to rule 9, it means that OQ equals to OT minus QT. Again, OQ equals to OT minus QT. Repeat again, OQ equals to OT minus QT. So OQ equals to OT, that is 16, it is the radius of the quarter circle, minus QT, that is R. So in total, OQ, this side OQ equals to 16 minus R units in its length. In the next step, I copied this right blue triangle OQM in a new page and implemented the Pythagoras theorem on this right blue triangle OQM. Okay, this is the right triangle OQM that I copied from the original drawing. The opposite OQ equals to 16 minus R. QM equals to R according to what is given as the question. It is the radius of the small circle. And finally, we already found out that side OM equals to 4 times square root of 2R. According to the Pythagoras theorem, in this right triangle OQM, OQ square equals to QM square plus MO square. Again, OQ square equals to OM square plus, again, OQ square equals to QM square plus OM square. Repeat again, OQ square equals to OM square plus QM square. So OQ is 16 minus R, the hypotenuse. Therefore, Q square is 16 minus R square, and it is equal to QM square, or it is equal to OM square. So OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square, plus QM square. QM is R, therefore QM square is R square. So according to equation 2, we should find out that 16 minus R square equals to 4 times square root of 2R square plus R square. Here open the brackets on both sides of this equation and equation 2, and finally found out that according to this equation and equation 2, 16 minus R square equals to 16 squared, that is 256, plus R square, minus 2 times 16 is minus 32 times R. So it is minus 32R, and it is equals to 4 times square root of 2R square. 4 times square root of 2R square is 4 squared, that is 16, and square root of 2R square is 2R, because the power cancels the root and the total is 2R. So this expression in total equals to 16 times 2R plus r square. Here we have r square both sides of this equation 2, so r square will get cancelled. After cancelled r square, this side of equation 2 we have only 256 times 32r. And the other side of the equation 2 we left with 16 minus 2r is 32r. So according to equation 2, if we found out that 256 times 32r equals to 32r. Here we added 32r to this equation 2, and we found out that 256 equals to 32r plus 32r is 64r. So 256 equals to 64r. Here we divided this equation 2 by 64, and finally found out that r equals to 256 over 64 is 4. So if we found out that the radius of this small circle r equals to 4 units in its length. Okay, thank you very much.